So we spent all of last chapter talking about ionic bonds, and today we're going to shift our focus on the molecular bonds. Remember I said that molecular and covalent bonds, they mean the same thing, and so the word covalent is going to come up much more this chapter than it did last chapter. So molecular compounds are made up of individual molecules. This is different than in ionic compounds. Instead of molecules, we called them formula units. Molecular formulas will show the quantity of each atom. So one of the specific types of molecular compounds is a diatomic molecule. A diatomic molecule is a molecule that contains exactly 2 atoms, and typically they are atoms of the same element. So hydrogen is a good example of a diatomic molecule. Oxygen is also a diatomic molecule. And these molecules are almost always found combined with another atom. So like you will not find just a single hydrogen atom floating around. That's not very stable. So it automatically will almost always be bonded to a second hydrogen atom if it's not bonded to another another element. So the energy and bond formation, if 2 atoms are far enough away, they just won't interact because they're too far away. So that makes their potential energy equal to 0. However, as atoms get closer and closer to each other, their electron clouds are going to start to overlap. If the electrons from the 2 atoms begin to repel each other, the potential energy will increase. If they get so close that the attractive forces develop between the electrons and the nucleus, the potential energy will decrease. So this gets shown in this little handy dandy graph right here. Up here, if we have a repulsion, it shows that it's high potential energy. If there is a little bit of overlap, we have low potential energy. And if there is no interaction at all, the potential energy will be equal to 0. So with that, we get a covalent bond. And this is a bond in which 2 or more atoms will share electrons. At this point, your potential energy is going to be at its minimum. So that would be down here. So we can show covalent bonds through a Lewis electron dot structure. This is a diagram of the structures of molecules that are held together by covalent bonds. So we can do this for 2 hydrogen atoms. These structures deal with only the valence electrons. So hydrogen has 1 valence electron. There's the Lewis electron dot structure for 1. Here it is for 2. Does that make sense? We did electron dot stuff last chapter, right? Yes? No? Yes? Thank you, Kylie. So, we can have a single bond, and this is when 2 atoms are joined by the sharing of 1 pair of electrons. And we can also show this in a structural formula. This is a formula that shows the arrangement of atoms in a molecule and represents the covalent bonds by using dashes. So this would be an example of the structural formula for the diatomic H2 molecule. If we did it with the electron dot structure, we'd have 1 electron from the first hydrogen atom, and then we'd show the other one with a second dot. So both of these methods indicate that there is a single covalent bond holding these 2 atoms together. So just like with ionic bonds, we like to follow the octet rule. Same as the ionic bonds, everything wants to be like the noble gases, meaning that they want 8 valence electrons. Save hydrogen. Hydrogen would only want 2 valence electrons. Single covalent bonds will form when 2 slightly occupied orbitals overlap with each other. Singly occupied, sorry. So that means that there's only 1 electron in the orbital. Each orbital generally holds how many electrons? Or maxes out at how many? 2. So that's why these 2 hydrogen atoms, they can bond covalently because they each have 1 spot for an electron yet. So fluorine also would have 1 spot left available. And so the only thing that has to be true with these bondings is the electrons have to have opposite spins. And since we're doing everything on paper, we can make that true. And so we don't really need to worry about that too much. So lone pairs of electrons are a pair of electrons that is not involved with the covalent bond. So we know that fluorine has 7 valence electrons. So when we draw the dot structure, 1, 2, 3, 4, 5, 6, 7, these are the lone pair electrons. They're not involved in any of the bonding processes, but they are still paired. So we don't worry about them. We just we'll talk about lone pairs. So that would just be a term that you need to be familiar with. So how the heck do we draw these Lewis structures when we have bonding? So the first step is to figure out how many valence electrons are present in the compound. So in this case, we're dealing with water. So we have 2 hydrogen atoms, each of which contribute 1 valence electron. So we'll get a total of 2 valence electrons from the hydrogens. Water has 6 valence electrons, and we only have 1 of those. So we have 6 valence electrons from oxygen. In the compound, we would then have a total of 8 valence electrons. So when you draw this, you need to make sure that you have 8 valence electrons in, or 8 dots in the drawing. So I'm going to do this color-coded, just so hopefully you guys can see it better. You do not have to color-code them if you do not want to. So for the first hydrogen atom, we can draw that with the 1 valence electron. Then we have our second hydrogen. Again, it has 1 valence electron. And then lastly, our oxygen has 1, 2, 3, 4, 5, and then 6 valence electrons. Notice that the lone pairs are as far apart as possible in the diagram. So then to draw your diagram, you need to pair up the electrons in the open spot. So this hydrogen has 1 valence electron and can be placed here. And our second hydrogen has 1 valence electron and it can be placed here. It fills the oxygen out to make a complete octet. Then we write the H's on the sides here. So just to rewrite it so it's a little bit more clear, we have 1 hydrogen that had 1 valence electron. We bond that with the oxygen. And then we take our second hydrogen to fill in that pair. And now you can double check that you have a total of 8 electrons present. 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 valence electrons, just like we need. Everything is paired up. That would be your second thing you need to check, is that there are no lone electrons, no single electrons. After you do these drawings, everything needs to be paired up. It doesn't matter if it's part of a bond or not, but you cannot just have a random 1 electron. Does that make sense? Yes? No? Okay, good. Sometimes some molecules cannot satisfy the octet rule with a single covalent bond. So an example here is C2H4. Again, if you look for total valence electrons, we have 2 carbons, which gives us 4 valence electrons each for a total of 8. We have 4 hydrogens, and that gives us 1 valence electron, so that gives us a total of 4. So here would be a total of 12. But if we do everything with a single bond, and one of these would come from hydrogens, how many total electrons do we have to fill the octet rule? How many total electrons do we have in this drawing? Try again. I count 14. Marta's getting 12 though. Do you see 14? Yeah. Okay, so there's 14. So according to our total number, we can't do it this way. So instead, we have to form what we call a double bond. So if you go through this process and you're like, oh, I've got too many electrons, that means that one of these unbonded or lone pairs needs to slide in here to form a double bond. And so when you do that, we can satisfy our octet rule. This would completely goes away because we had too many electrons. And so notice how we don't have any lone pairs. Everything is satisfying the octet rule, and we have our 12 electrons. So we can do this with double and triple covalent bonds. If it's a double bond, it's sharing 2 pairs of electrons. If it's a triple bond, we're sharing 3 pairs of electrons. You can either use the dot method to show these, or you can do the lines with the structural. This would be a single bond, double bond has 2 lines, and triple bond has 3 lines. Any questions? Okay. The most important thing for you guys here is you need to pay attention to the correct number of valence electrons. Don't just get dot happy when you're drawing these. You need to make sure that that the number of dots corresponds to the total number of valence electrons.